Okay, hello, Stephen.
Hello, Professor.
Hello, Vova. Hello, Amir. Hello, Sarah. Hello, Boston. Hello, Lina. So, thank you for investing your time into the course and for getting your votes about presentations. This year, we are going a little quicker than previous years, so I appreciate your effort to give more time for projects. So I will just open the list of subjects and check what needs to be covered. And if there will be no specific questions, my intention. Is someone speaking? Or should I feedback? Okay. So if there will be no questions on my own things related to concept of speed and metal organic complexes with open shell configuration. So in some sense, we did nothing new in principle. We already got the skills how to prepare model, how to run organic structure, how to look on the energies, and how to analyze the orbital and basic states. But there is an important aspect. In 90% of practical computation, and in everything that we do at the moment, the number of electrons in all of our models were even. Electrons were paired, right? You remember in the titanium hydroxide single titanium, the number of HOMO was 24. Not 23, not 25, 24. Because all occupied orbitals were filled with paired electrons. And for large number of stable structures, it is true. The paired spin configurations are often preferred, but not always. There are some exceptions. And, if you are working with devices for information storage, or if you are looking on catalysis in these metal organic complexes. So it should be. Oh, hello, Steven. Nice to meet you in person. I'll continue with metal organic complexes, but Steven, a short message to you. If you're viewing, you can present on Friday on a specific subject that was prompted by your advisor. So if you summarize skills, how to do projected those in Gaussian. I mean, you can do it even shorter than everyone else, like 3 minutes, 4 minutes. Would you feel comfortable doing this? Okay. I'm not going to present it. It's you should base it on your. You should teach us, not us teach you. Okay, so. Metal organic complexes, which are typical objects for inorganic chemistry and for catalysis, often use the transition metals from the middle of periodic table. And metals often like to take alternative configurations with odd number of electrons, odd not in the common sense, but odd like not even. Are going to go ahead of lecture materials about week and a half. But later on it will be covered in lectures as well. So if the number of electrons is odd, there are, I wouldn't say dramatic, but noticeable changes in overall methodology. So if the model includes non-equal number of spin substance in down, one needs to solve it as two models. One is only spin up, another is only spin down. So the number of orbitals doubles approximately. If there are specific balance in Gauss view or specific options in preparing non-line input to address it on one hand. And on another hand, the density of states and orbitals, as well as affinity and ionization, should be computed with an account of this subject. So I'm going to pursue this direction and basically repeat what we did last time, but for a model with odd number of electrons. So preparing model, make computations, look at ionization, affinity, and then for the density of states and form. I think it will be kind of revisiting the skills that we already had. Before we go there, we stop the editor because I'm too excited about the material. Let's revise what are our presentation subjects. For those who are online, so there will be subject number 6, Stephen partial projected risk, or we can skip it, or we can do it for so right now I observe that all subjects are quite doable. There are no big challenges, but there is a little challenge to number 2 for Vola. And after I'm done presenting what is planned, I will stop by and we'll talk about your presentation. But generally, let me tell by words how one can do, how I will do your presentation at your place. So you may observe that on some platforms, like on Mac computers, Gauss view is not reliable if you do it remote. Even today, I was trying it from here. It was not as reliable. It was stopped working, and then it's not right. It's not comfortable for doing productive research. So the interaction between human and actual calculations through this graphical interface is not a high throughput. It's arrangement. It's only the introductory steps for learning basic concepts. In fact, everything we do can be done by typing texts in command line. And I'm not urging you to do it always, but be ready to do it just in case to be independent. And whenever you submit a Gaussian job, even through Gauss view, you may have noticed that it asks you, would you like to save input file? You remember it? And you give the file a name. So, and then you tell submit it to Gaussian. If at the same time you will try to go back to your directory and open the file that you are submitting to the Gaussian.com file, you will see text codes, some abbreviations for anything you plan to do. So it converts your clicks of mouse into text. And this text keywords are not very long. Some professionals are able to memorize them, just type them as we speak. So suppose that I know nothing in the subject, I just came here and want to make a presentation on the subject. What I would do, I would inspect the jobs that I was already submitting, and I would look into the files, .com files, and look on their first maybe 3 lines, and try to find trends, what is being told there. Try to interpret and then deliver my observations to the class, to the peers during the presentation. While doing it, maybe some additional options will pop up, but maybe I'll quickly show it so that everyone feels comfortable. Because when we start this new thing about spin, it will be so exciting that I don't know about you, but I may forget about everything else. So let me go back to the, and if you're bored listening to me, you don't have to listen to me all the time. Just log into the Photon server, make a directory for Lab 7, open GaussU, and on one hand or another, open PowerPoint and start preparing the slides. Right? Maybe it's better investment of your time rather than listening to what I'm mumbling. Okay, so going back to last time was 6, right? Oh yes, today is 6. Thank you, sir. So last time it was 5, and so I'm looking for all files that end with .com. And yes.
No, Professor, I'm just trying to see that what's your writing.
You don't see what I'm typing?
Yeah, I'm able to see right now. Yep.
Okay. So I can type more, and the .com file that we were doing on the previous slide. And here there are some keywords. So for the first 1, 2, 3, 4, 5, 6 lines, there are some keywords, and after there are positions of ions in like Cartesian projections. So basically, what is shown here is what is being asked for subject to prepare a Gaussian input as text to compile. So what should I do if I do have Cartesian coordinates, but I do not have Gaussian program? Then I will create a file and add these keywords. And depending on what I need, the keywords will be slightly different. So the first line here showing where to store intermediate data that later we use for molecular orbitals, right? So check equals this check file. Then after this number symbol, it shows the method and basis set. Right? Those are most. Yes.
The number symbol, that's just commenting on that line so that you can have after that whatever you want.
Mm-hmm. And the next important thing is this in line number 6, 0 and 1. So as we will see in our today's exercise, the meaning of these two numbers are so-called charge and multiplicity. The typical and standard values of these numbers are 0 and 1, which will go if we look for neutral molecule with all spins pair, which means single state. But if you are going to some odd number of electrons, these numbers will be modified. I'll show you. So in very brief, it is the subject of your presentation, but you'll better look in a little bit more detail. Okay. Yeah, thank you, sir, for catching me on being bad in arithmetic. I thought it's already 7 because the subject that we are going to cover in previous years was 7. So we are doing a little bit quicker. So, yes, Kay, you were about to say something?
Yeah, when I typed CD test /
No, you should.
maybe I don't have anything like that.
I am in my directory. I did create this test subdirectory.
Okay.
If you in your directory, you do not see it, so do not follow me literally. Right?
Okay.
So please raise your hands if you ever had inorganic chemistry as a big course, or thank you, Stephen, or as maybe part of any chemistry classes. Okay.
I had high school chemistry.
Okay. Okay. So we could do this example with our previous studying sites, but I suggest you practice this model, and in a minute I invite everyone to draw this model because we will permit to. So what is the difference and what is the meaning of this model? Yeah, I will take microphone later. I didn't bring it closer to the dynamics, otherwise it will create feedback noise. So this is the model we started last time, right? And here the titanium takes oxidation state 4+ and hydroxyl group state minus, right? So in total, the balance of the ions will be 0. So total number of positive and negative charges is 0. So it's a neutral number. And it is arranged with 4 ranks for ligands. They are arranged in symmetric tetrahedral. As in freshman chemistry, there is a little demonstration when one takes 4 balloons, connect each one with a little rope, and pull it through the ring. So they automatically arrange in most preferred spatial direction. step that I'm going to show now appears if one takes titanium chloride and dissolves in water. It's not a material of most technological importance, but it's one of the simplest examples that can model easily. So in this titanium 4 and 3, minus, 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 and then it has 3 plus, right? And when one dissolves this in water, it dissociates. The chlorines, 3 chlorines are floating very far away, and the titanium 3 plus attracts water molecules to coordinate with it. And just by the matter of fact, it is able to attract 6 water molecules. So it's quite stable configuration in the solvent. But if you forget about these chlorines and look only on this object, right, the overall charge will be what? Oxidation will be neutral charged. Yeah, 3 plus. We can just pull this 3 plus and put it here. So basically, we are going to look on this compound, and what should be. So this is a little fragment is marginal. So neutral titanium configuration has like 6 electrons on 3p, and the next last 4 electrons on 2 electrons on s orbital and 2 electrons on d orbital. Right? If one ionizes it, if one creates a complex where 4 electrons are withdrawn, then one takes away this 4s and this 3d electrons. So it has only closed shell with p electrons. But if one creates 3 plus instead of 4 plus, then there is 1 extra electron on the d shell. So and this will be electron up. All other electrons are up and down, compensated, and 1 uncompensated. Right? So there will be 1 spin, 1 unpaired spin, and if there are no strong magnetic fields, there are equal opportunities for the spin to be up or down. Right? So you have 2 possible orientations, like up and down. There are two configurations, and the 2 means double. Therefore, one poses double. Whew. I don't know about you, I'm already tired. So let's try to model the situation and see what happens. So in the Gauss U, if you can open new molecule, then let's try to build it. And you can do quicker than I did. So select titanium, and then you see this different orientations. So last time we did tetrahedral, and now we need octahedral because there are 6 neighbors, and we want them to be symmetric. So I click once in the middle, and then I select oxygens, and I can just click 6 times. Do not worry that it shows hydroxyl. We'll fix it in a minute. So hydroxyl, and instead of hydroxyl, it should be oxygen. Or it should be water. So I'm just clicking on hydrogen and put them each. So I select hydrogen and select it to be in atom, and click it 6 times near each oxygen, and then quickly establish a bond just in case it needs to be force field optimization. So right now it is a freestanding hydrogen, and I set up a bond, just single bond. So right now it is chemically correct, but aesthetically ugly, and I want to save it as handwritten titanium 6. And maybe I might try to optimize it with clean, which may or may not work. And then also it's my own decision whether I want to further optimize it with UFF, with force field. I may decide to further optimize it. And although I'm doing mechanics, it already asks me for charge and multiplicity. So the charge is 3 plus because it is a stable configuration. So each of the waters are neutral. Titanium is 3 plus because it inherits it from titanium chloride. So overall 3. And then after I start.
Why you change the charge? Can you repeat again?
Yes.
Sorry, please repeat again because.
So the complex that we are describing originates from solving titanium chloride in water. Titanium chloride has titanium oxidized. Titanium has lost 3 electrons. So it is 3 plus, which means 3 electrons have been removed compared to neutral metallic titanium. And after you set up this charge 3, yes? So if you bring an option to select between spin, and it will show this options of doublet quartet that was different compared to neutral, right? And we select doublet because the one electron can have only two orientations. Let now we do job type optimization, mechanics, submit, save. UFF, submit to Gaussian. Okay, and it's ready. So maybe it's slightly modified the angles. And right after this, oh, by the way, if I am preparing talk number 2, I can immediately look into this files. And it shows an example what is changing if I so if I use force field optimization gives this keyword. UFF means the inverse of force field, and this two numbers correspond to total charge and multiplication. It's written. Remember when we had neutral with paired spins, it was 0, 1. Right? Okay, now I'm going back to Gauss view. And my next step would be to compute electronic structure. So I'm going to Hartree-Fock. I'm changing the basis set to whatever is reasonable for transition metals. And I know that Kaya will briefly cover basis set subject in presentations.
Okay.
So and
Struggling with the laptop, Professor. You need to go slowly.
yes. So and later we will cover partially basis sets in class, but if you see the one that we're using right now is a little bit far from the beginning. So typically, if one looks into the textbooks and basic explanation, they cover simpler basis sets. Just right now, we're not going to speak because it's an important subject, but we select whatever is optimal for this model. And instead of optimization, I select energy, click submit, save, until so I'm doing Hartree-Fock, and then okay, let me walk through the sheets and make sure that we are all on the same page. And you see this calculation goes quite quick. Oh. For some reason, I think we do not have this picture.
No, I'm just following this.
Oh, okay. So you're like advisor.
No, of course not.
You completely open the structure of the use Yes, you'll do. Right. We'll do this common manage. This next step. What's the reason for this?
restricted network related and did not create optimization for chip. This year, we didn't realize that. So this was chip.
Church and more.
Yeah, but then we also changed the we also changed the I changed here also. And I'm looking here the more positive thing the particular direction.
Okay. So I'll answer the question of law and then check how Kay is doing. So
Professor, I need, please give me permission for sharing my screen.
I'll answer question of law and then we'll be with you. So Law was asking why it is automatically selected and understood. So formally speaking, all calculations can be done with understood calculations, but in case number of spins up and spin down are equal, unrestricted gives the same result as closed shell. So and to save computational time, this unrestricted option is not checked in regular calculation. But if number of spins is unequal, then one needs it and goes through prompts this time. If you will look into the input file that you just submitted, instead of HF, it will show UHF. Unrestricted, it means that it allows to track independent spins up and spin down. Make sense? Let me ask Kaya. Let me ask Kate, would you please share screen just to show where you are?
So this one after optimization and then just a minute.
Good. Did you submitted the?
Yes, I already submitted.
Okay, can you click on the results? Quick.
Just a minute, Professor. Oops. Okay.
File type. Oh yes, that will be.
So here I did one mistake, and now I'm able to understand that you restricted there. So I didn't do that. So I need to do that again. There.
Okay, but I see the three doublet. Yeah, everything is good.
Yeah, but one mistake that I forgot to.
If you do it through Gauss view,
yes.
It fixes if the human forgets to do it. So if you put the charge value uneven, a charge value not equal to 0, then it prompts to make unrestricted automatically. So everything is good at your side. Okay. So yeah, you can stop sharing.
Okay. Professor, you did something on you write something here, so I missed that part. So
I'll show, but I don't think it was anything.
Okay, what you did?
I just watched the file.
Okay, .com, and then you want to.
Yes. So now after everyone is on the same page, I am inviting you to repeat the steps that we did for understood. So there will be 3 steps: analyzing the dot log file for energies of orbitals by human height, plotting molecular orbitals, and making density of state.
Sorry, what I need to do?
Just I'll tell what to do.
Okay.
I'll show you. Okay. So first, I'm just blindly opening and scrolling through the .log file. And
Dot log file for Professor, dot log file after energy.
Yes, after not
Okay.
not optimization, but after energy, single point energy by Hartree-Fock. And I'm looking for the list of orbitals energy with occupied and virtual.
Yes.
And you see here there is a little surprise. So I'm about 43% through the file. Okay. And there are occupied and virtual table, but there are 2 tables of those. So one table occupied and virtual alpha, and another, if I scroll further down, it will be occupied and virtual for beta. So alpha and beta stand for spin up and spin down. And let's focus.
Why? Sorry.
Yeah, okay, I'm listening.
Yeah. So why there? Before, when we did the same thing, we have just only alpha occupied and alpha virtual, but here now it's beta also. Why? We have 2.
Because we have spin up alpha and spin down beta. Before we were believing and assuming that beta electrons will repeat the same pattern as alpha. So since at each orbital we have 2 electrons, alpha and beta second electron will have absolutely the same energy as alpha electron. Right? Now when they are not equal, number of electrons is not equal, there are independent width for electrons with spin alpha and electrons with spin beta. So if I'm looking for total number of occupied electrons, so it's 5 rows and 2, 3, 4, 5, 6, 7, 7 columns, right? What's the total? 5 times 7. How much? 35. So 35 occupied alpha electrons. And then HOMO is -1 atomic units, WOMO is -46. And one can write it down and subtract the difference, which will be the difference will be atomic units. Now let's look on the beta electrons. So 5 rows, 5 colon 7 rows, but the last row is incomplete. So total number of beta electrons is 34. And the numbers, I wouldn't say they're so much different. They're close, but let's check if they're literally the same or different. So it's -1 0.10 and minus 0.44. What's the gap? Huh?
Around one.
Yeah, so it is bigger. Right? So the gap for alpha and beta electrons is not the same.
What is the thing of the
Minus 1.10. This one. So we are looking for the last one in the range of beta occupied. It's HOMO, and the first one of beta virtual is here. Okay, so we see that there is something unequal. And if you do not do any graphical information, then for ionization and affinity, we select the highest out of homos. If there are two homos, we select the one which is bigger. And for affinity, we select the lowest of the wounds. Right? Because if you remove or add to the system, it will automatically find the it will flip the spin just to match the better energetic calculation. Okay. Now there are two more things which will take more time. The orbitals and density of states. So for orbitals, we need to do the same thing as we did before, like form check and then cube gen, right? With the only little modification. When on the last slide you were using cube gen O and then putting molecular orbital equals something, now we will put the words AMO and BMO for alpha and beta molecular orbitals. And they will, even for the same number, they will be. So I'll practice it right now. In addition, this way that I'm going to demonstrate in practice is more reliable, but less complicated. There is a much quicker way that I will not show. You can find it, figure it out yourself. And Kaya will present it during her presentation. She already found it. So there is a way to plot orbitals with like 5 seconds without typing any commands. And I'm not showing because it is not as practical for me because, for example, if I need to run 100 calculations, there is no chance to do everything by mouse and it's graphical. One still needs to do things in the command line. But just be aware, and maybe if you have curiosity, you can try to find it or ask Kaya or wait until she makes her presentation. So I do have this. So instead of log, I need CHK, and in front of it, I type form check. So also in the previous model, most interesting orbitals were number 24 and 25 because they were common to. In this model, most interesting will be 34, 35, and 36, right? Because they are homos and lumos for alpha and beta orbitals. So if I want to explore this model, I will probably draw 4 or maybe even 6 orbitals. 34, 35, 36 for alpha and beta. No, I do not trust my my memory about using the cube gen.
What you wrote?
It's my little prompt to myself. And also, let me show something.
You.
I can copy it to everyone, but if you are doing it on from different account, you will not see it. For example, if you log in from to CCAST, you're welcome to copy anything from here, but chat, copy the chat line.
Okay.
And in the online, again, if I do not count my memory, I can ask cube, Gen, Gaussian. There is a manual at the website of authors of this software, and it just tells all possible keywords, and they may give some examples. Sometimes it's just too much, but if you are lost, you can find it online. So it's not a big secret. Gen 0 AMO equals 4. Then I need to give the yes, this one. Gen 1. So I'm putting number 0 for single orbital, atomic molecular orbital 34, name of the input form check, name of the output, which should be self-explanatory, and then click enter. You see the creation of the cube file takes a little longer than actual calculation because it's noticeable number of grid points. And I'm going to systematically do it 3 alpha orbitals, and then I will do 3 beta orbitals.
What?
And after it is done, I will try to look how they to put these orbitals, and maybe if just in case, I'll probably copy paste images to the PowerPoint, just in case if I ever need it. So, type of file cube, molecular orbital alpha 34, surface contours, new surface. So I'll do this exercise and then make over a trip over tables, but I want to do it myself just to make sure that comparison is favorable and make some demonstration. But you don't need to wait me. Please try to practice the same things. If you don't have any problems, you should be able. So I'm done with alpha orbitals and now I'm going to beta orbitals.
Mm. Okay, now it's okay.
So I'm going to walk over the sheet. So, since each of us was doing independently and geometries may slightly differ, results also may be different. There could be some healthy and unhealthy errors. But if one is trying to probe the unoccupied orbital with very high index, I'm not sure about WUMO, but if I will take like WUMO plus 20, there is a high chance that the orbital will be not localized on a specific path, but will spread in space a lot. This means that the electron is not anymore the electron of such high energy before the experience desorption. So its energy exceeds the attraction forces of ions, and it's just free electron floating around. And since this orbital is unoccupied, this is quite normal. So it's, in some sense, illustration of a photo effect. If you heat it with photon, promote it up, it becomes not associated with the molecule that's spread in the space nearby. Make sense? I'll use just
We can.
Oh, it's only minor because I don't do it's like a little prompt connection in this field. Changes. Small number. They do it. Yes. Yes. Where did they put it?
Yeah.
Okay, yes, yes, maybe push it. No, yes, yes. Kay, would you like to share your screen?
Yes. Oh. What? Professor, when I okay, so there's error for that. This one.
Yeah, I see. Please do ls minus ot. ls space minus ot.
What? Yeah, those
Yeah.
things.
So can you hit arrow up just so that I see your previous comments? Arrow up several times. Up, up. Stop. Back. arrow
Back.
down. Yeah, let me form check lab 6 18 energy cut. Okay, hit enter once again. Yeah, looks good.
Then write the cube gen, that one.
Okay, just wait. Hit arrow up once again. Once again. Stop.
Okay.
Now do arrow left. Arrow left.
Left.
But yes.
Mhm.
Stop.
Okay, stop.
Twice more. Twice more. Arrow left. Arrow left. Now add right. Arrow right.
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 Okay.
Now type the letter F.
F.
F like 5. F
Okay.
like 8. And now hit enter.
Oh. Now I understand. Okay.
Now type
So
ls minus lt. ls space minus lt.
this minus LT.
Enter. Now you see you have this AMO cube. And you now let's open it in Gauss and make sure that it works.
Tab in.
No, you have Gauss you open. You do not need to reopen it once again. You already have it, right? Click here and make file open. File open.
Just
Open.
in
File type. Click, select cube.
this one.
Or no, not check. Next cube.
Cube.
Over. One
Yes.
over. Yes, cube. Select this one.
Open.
Okay.
It takes time. Okay.
Now
So
shift it to the right so it doesn't block main window.
then
And results. Click.
yeah, I already clicked.
Yeah, I understand the doings.
Surface control. There are 4.
4 or even 8.
Okay. 4. Okay. Yes.
Okay. Surface action.
Yes. Surface action. New surface.
Mhm.
New. Then
Okay. Yeah.
so
That's
now
it.
do the rest of the part.
And then repeat the rest. But it should work.
Yeah. I
Okay.
forgot.
Make sense?
Thank you, Professor. Thank you.
Oh, my pleasure. Okay, you may stop sharing. Yes. Do not worry. It depends on the individual configuration. You optimize it differently. It may so we are about to finish about orbitals. Let me add a comment that you may enjoy. So here is it doesn't like this writing. Alpha molecular orbital 34, 35, 36. I think it is too much of the load for this computer. And here is our beta orbitals 34, 35, 36. So the meaning of the orbitals with the same numbers is different. So for alpha and beta number 34, they are both occupied. They look similarly. They both have electrons on the p orbital of oxygen. And for the orbital 35, for alpha and beta, they have similarities in the shape of orbit. They both have majority of electron on the titanium. But for alpha, it is occupied, for beta, it is unoccupied. And then for 36, again, they look similarly, and they both are unoccupied. So the main difference is here. And the labels, the namings of this orbitals, I would say here is HOMO alpha, and this one will be LUMO beta. This is HOMO beta, and this will be LUMO alpha. So the orbitals of different index play the role of HOMO and LUMO depending on whether we are speaking about alpha or beta element. Make sense? Okay. The last part of today's program will be to summarize this information in form of density of states. So again, I do not count on my own memory. So here is a little manual. I believe it is also shared with you in the email, but just in case it is here. And the procedure is the same as you were doing in the previous lab. So we practice Perl script to extract energies of orbitals into separate file and to build the quasi-continuous distribution of density of states as we were defining before. There are 4 parameters: how many grid points along this line, what is the width of artificial width attributed to each individual orbital, which has 2 meanings. First, it is approximation to a delta function, bringing a finite width, because human eye will not be able to see zero width of the function. On the other hand, most materials are explored at non-zero temperature when there are sub-levels due to vibrational motion. And approximately this value corresponds to thermal energy. Then window in the energy range, how many more than was before and after the common tool. And then, unlike the similar protocol for closed shell, we are doing this procedure twice. So it may be not the most elegant programming, but it works. So we do it once for alpha electrons, once for beta electrons, then we copy it into a standardized name, and then we run the loop script that creates the PDF or script and then PDF file with this script. So I'm going to practice this protocol by this renaming the file name here. So in my little memo to myself, it was something different. Today I will take the log file that we just generated. And just in a second, I will copy paste this line to the chat.
Okay.
So after we do this little exercise today, I believe it will be not a big challenge for you to complete the homework, which will relate to singlets, not no spins, right? Check.
Thanks.
Pleasure. Then I repeat the same thing. It's just replacing word alpha to word beta. Let me copy it into the chat line once again, just in case. Copy. So there appear new files, and I just want to act a little quicker today than last time. So I'm going to copy into standardized name, and it is needed so the next step script can comfortably read the file, because so you use the same file name. And, I will copy it into chat line as well. Paste. But Kay, while practicing, note that names will be different in your case. Okay. Now I'm doing this, inspecting the files that were just created, and I see there is a DOS alpha log and DOS beta log. If by some reason you do hate GNU and you love Microsoft Excel, you can just download these two files, or if you have license to Origin and put them. So it will show density of states for alpha and beta elements. But I'll offer a little script that will combine them together into one figure. And after I'm done with demonstration, I'll make a 2/6 so that we all on the same page. So all files here, all the scripts are open for reading. They also are open for writing, but please do not modify them. Otherwise, you will screw the next year class. But if you need to copy, feel free. It's not a secret. And the scripts are also quite, especially the GNU scripts are like maybe 3 lines, really simple. So after executing this script, we do see the PostScript file. You may want to convert it into PDF, and then one can download it to the local computer through this left panel in the Wobeck's term, which is equivalent to Venus CP. So it is a message for Steven. So Wobeck's term includes both PATI and Venus CP functionality. So here is the image that I was planning to do, and it's really this image and the orbitals should complement each other. So the upper side of the image is density of states for electrons with spin up or spin up. The lower part that is oriented down is density of states for electrons with spin down. And we see that the gap for electrons with spin up and electrons with spin down is different. Okay. So I believe let me copy it into PowerPoint and then analyze a little bit more. So, it will take additional 30 seconds of delay, but after it will be quite reasonable to analyze. So you see that each peak in the density of states can be interpreted by associated it with one or another orbit. So typically, those are occupied are correspond to orbitals localized on oxygen. Those unoccupied correspond to those localized on metal, titanium, and this for general term for any oxide. And for the orbital number 35 is outlier. So it is appears as a impurity defect statement inside the data. So although it is a molecule or a solid, one can also describe it in the language of impurities, defects. So let me walk through the seats and check if you are able to prepare this density state. After we are done with this, I'll check if there are any questions about the presentations. And as a little announcement about presentations in Friday, I hope Stephen will make a presentation on so-called partial density state, which will be an additional tool to interpret the molecules. So here we make separate treatment of alpha and beta electrons for different density states, and Stephen will teach us how to do different density states for electrons that are localized on oxygen. So it will primarily only this occupied. Then density states for all electrons, for all states that are localized on titanium, they will primarily here. And maybe all electrons that are localized on hydrogens. So for molecules where it's hard to draw orbitals, it will be another way to interpret the
Professor,
Yes.
thank you for sharing those comments. I already use those things. Then after that, how can I? How could I get that figure?
Oh, I didn't share the command for. Let me share the command.
That 3 lines. 1, 2, 3.
2 lines.
2 lines. Maybe that the first one also I need to write. I don't know. Maybe.
Oh, you only this two.
I don't need your US spin dash G09PS. I don't need that command.
But I did send it. I did send it to you as well.
Thank you.